Okay, hi everybody. This is a really important result. It's about geometric series. I don't know why it's called this, but this is what people call it. And what does it look like? Well, for any two complex numbers, you just pick them, then you can create this sum where you're summing over the little n's. N equals 0, 1, 2, 3. So it looks like a plus az plus az squared plus az to the third plus forever and ever. Okay. Explain when this series diverges or converges. Okay, so to start, the divergence test will tell us when it diverges. So that's nice. Whenever this complex number z that we chose if it's even greater than or equal to 1, in other words, like in the complex plane, here's the unit circle. If z is on the unit circle or if z is out here, either of those, if we just keep raising it to a power, if we're out here, it's going to keep spiraling out and out and out, much bigger, and it's not going to go to 0. And if it's here on the unit circle, it's just going to spiral around in some way, and it's not going to go to 0. So if this is true, then the terms, namely these terms, do not go to 0. By the way, go to means they do not go converge to. So this is just another way that people say it. So thus, this infinite sum does not, or we'd say I was going to say it does not exist, or we could say it diverges. Because I guess that's the word it used. Explain when this series diverges. Or converges. Now, when will it converge? Well, the divergence, if z is strictly less than 1, in other words, if we picked some z inside the unit circle over here, we picked a z like there or there or there, then the divergence test doesn't tell us that it diverges anymore. We still don't know if it converges. Well, now we're going to prove it. And actually, this is part B. Already we're going to just compute the sum when it converges. It turns out that it'll always converge when we pick a z that's somewhere in that unit circle. If z is less than 1, the divergence test is silent. So we look at partial sums. Right? This symbol here, an infinite sum, doesn't actually mean that we're going to add up infinitely many things. It means, does the sequence of partial sums that we can actually do, does it converge? Well, let's look at the partial sums. S sub m, let's call them. Well, it's C, well, okay, we started at C0 plus C1 plus C2 plus, now let's go to Cm. So that's a times z to the 0 plus a times z to the 1 plus a times z squared plus dot 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 plus a times z to the m. Right, I'm just using what our particular geometric series, they call this a geometric series. It looks like this. Okay, so let's investigate this. First of all, when you can factor something out, definitely do that. Z to the 0 is 1. Okay, so this a is just going to hang out. It sort of is irrelevant. I mean, it'll come into the answer, but it doesn't really affect anything. And what we need to look at is this piece. What's going to happen here? Now here's where we have this very important and just worth remembering how to get this algebraic identity. If you multiply this thing by 1, you'll get, well, obviously this thing again. And if you multiply it by z, you'll get a shifted version, right? If you multiply by z, this 1 will become a z, this z becomes a z squared, this z squared becomes a z to the third, etc. The z to the m becomes z to the m plus 1. And then let's subtract. So over here, I'm just going to say that if I do 1 minus z times 1 plus z squared plus z to the third plus blah, 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 plus z to the m, what happens is the 1 comes through and just gives me all these things again. But then the minus z comes through to everything, right? Just like the 1 came through to everything. The minus z comes through, and I get, oh, I'm tempted to write minus z right there, but I'm going to shift it because I notice what's going to happen. Look at that. The minus z finally hits the zm, becoming a minus z to the m plus 1. And so at the end, we get just this. All these terms cancel, and we just have this and this. And so the identity, very useful. It's very useful to note that 1 plus z squared plus blah, 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 plus z to the m is equal to like that. I just divided through by this, and so it went downstairs here. Therefore, we come back over to our partial sum, the nth partial sum, and we can write I guess I'll put it in parentheses. Okay? Since the absolute value of z was strictly less than 1, this part here goes to 0. Goes to 0, you know, as m goes to infinity in the natural numbers. Right, as m gets bigger and bigger, the powers of this shrink and shrink, and they go to 0. And that is what happens. Now, we've proved this before, so we don't need to prove this part again. This is now sort of accepted fact. Accepted fact. Because we proved it before. Okay, well then, the limit of the s sub m's is just the limit of, well, s sub m is equal to this thing. Which is just the well, okay. Now the limit sort of goes inside here. The only thing that has an m in it, this is the limit as m goes to infinity, I suppose, is this thing. And so we get a times 1 minus but this whole thing is 0. So the sum, and in conclusion, if the absolute value of z happens to be less than 1, then the sum, the infinite sum, converges to this complex number, right? Amazing. This part here is the most important part of this problem. I will just put it in a thought bubble. You might think it's not important, and you would be wrong. So this is the most important part. This allows us to, in this case, simplify that to here. But I promise you, this will show up again and again. Think about like what we're doing here is sort of a very simple algebraic pattern. Just like the simple algebraic pattern of a plus b squared is very useful, and a minus b squared is also very useful. And these patterns have come in and they've allowed us to prove things about arithmetic and geometric means, and this algebraic identity, I guess maybe this form of it, is extremely useful. Okay, we explained when the series diverged or converged. It just depended on whether this z that we chose, this complex number, was greater than or equal to 1 in modulus, then it diverged. And if it's strictly less than 1, it converges to a over 1 minus c. This is the conclusion.